with all the curves that are going to be the overboarding gradient, the pore pressure, the shear failure gradient, and the fracture gradient. And then I'm going to finish with some personal conclusions about the topic. Okay, millions of wells are drilled every year, and most of them use geopressure stats to be designed. It is important to have in mind problems in relation with geopressures of the drilling wells, and these problems are going to be common when the geopressures are not known or when they are not well estimated, and this can lead us to operational complications such as blowouts with a total loss of the casing, without mentioning the economical losses, and even worse, the human and environmental losses. So, well, I might put in here some images that belong to that Deepwater Horizon drilling rig that was in charge of British Petroleum, and as many of you may know, it was from the Macondo well. That is the worst disaster with oil spilling in the Gulf of Mexico since the Valdez in 1989. So, well, the reason I put it now in here is because the problematic in that well was related with geopressures, and it was in a simple stage. Well, now the geopressures are gonna involve all the ground existing tensions and pressures that are imposed to the formations and can lead them to rock failure. And also we are going to be working with this geomechanic term, that it's going to be a model that studies the rock mechanic properties and the behavior in the physical environments due to pressures and tensions. And well, in order to obtain our pore pressure, our shear failure gradient, and our fracture gradient, we need to also calculate with them the density of the drilling fluid, that it's gonna be the one that rules the pressure inside the well. That is the importance, and also the shoe casing placements. So, well, now I'm gonna show you the typical workflow that is used in order to obtain a geopressure model. And this is going to start, like in many geological studies, with a data acquisition that it's going to be needed while we are in the area study, or with previous studies with correlation wells, are going to give us information that it's going to help us to obtain the formation's density. And now, once we have this formation's density, and with some other calculus such as the Gardner equation and the Millers, we are going to be able to obtain our overboarding gradient. This is going to be our first entrance data in the geopressure model, and with it we are going to be able to calculate the pore pressure. And then in this stage is when we add the mechanic rock properties and then its tensions, and these last two are going to help us in order to obtain our fracture pressure and our shear failure gradient. So now the first pressure, as you can see for model, well, these whole data, it's gonna be calibrated, and they are gonna be need geophysical well logs and seismic velocities in order to obtain them. And it is also important to have in mind that are gonna be work in terms of gradients or pressures, and this is because our comparison parameter, it's gonna be the pressure exerted inside the well by the drilling fluid. Now, the first gradient is going to be the overboarding gradient. And this is very important because in order to have it, in order to calculate the other pressures, first we need to establish this one. And if we establish it right, we are going to get better results for determining our pore pressure and our shear failure gradient. So, what is this overboarding gradient? The overboarding gradient is going to be the pressure exerted by the columns that are above a specific point on depth, including the water layer and the overlaying layers, their density and their weight. So let's imagine I'm at depth 6 here. I'm gonna estimate, I'm gonna consider my water layer plus the density in the layers that are above my layer 6. So with that, we are gonna get this curve in here, that it's gonna be my first curve in the model, and it's also gonna be a boundary. Now, the pore pressure, it's going to be an next pressure that is used for this model, and this pressure is the pressure exerted by the fluid inside the formation that can lead also it to break. So this is important slides in the fact that it's going to establish the density of the drilling fluid that it's going to be necessary for considering the pressure inside the well. And well, this is going to be marking here with this red curve. There are going to be two scenarios in this here pore pressure. That it's going to be when the pressure that is exerted inside the well is major to our pore pressure, we are going to have an influx, and in worst cases a blowout if it reaches the surface. And on the other hand, if the pressure exerted by the fluid outside the well is major to my pore pressure, I'm gonna get a stuck in my drilling pipe due to differential pressure. These problems are both related with this kind of wrong estimation of the pore pressure and are gonna be very common in our well drilling. Now, well, the types of pressure that I could face while drilling are gonna be my normal pressure, my under pressure, my high pressure, and my over pressure, but the ones I'm gonna carry for are gonna be just my high pressure and my over pressure. And this may be by some reasons like in-situ tensions due to tectonics or subcompaction, and also are gonna be by fluid expansion due to temperature rise, free water, and hydrocarbon generation. Also density differences by the buoyancy effect. And finally, by lateral pressure transference or fluid migration. Well, in theory, I can estimate these pore pressure by the logs of the porosity logs. That are going to be my sonic log and my resistive log. I'm going to make a trend of convection with some other formula that are going to let me calculate that pore pressure. And here it's going to be the pore pressure as I showed you before. And now, this pore pressure is going to be calibrated while drilling with some well parameters such as the drilling fluid, the rate of penetration, and also some formation tests, just as XPTs and MDTs. Now for calculating my shear failure gradient and my fracture pressure, first I'm gonna have in mind the tensions that work around my well. And these tensions, once I get them, are gonna help me in order to don't reach them and my well could collapse. So, this shear failure gradient, it's gonna be that pressure that it's gonna lead the rock to failure due to shear, compressional tensions. But in simple words, it's the minimum necessary pressure in order to break my formation. So I might have it by two reasons. That it's gonna be a low drilling fluid weight that it's gonna lead me to an inferior shear failure, or by the other hand, due to excessive drilling fluid weight, that it's gonna lead me to a superior shear failure. And I can see here a great example of this in my well diameter. While I'm increasing this shear failure, it's gonna be a deformation in it, and it can be shown by the breakouts and tension fractures, such as I'm putting here, and also by the deformation of my drilling pipe. Now, it's going to be represented here in my model with this green curve, and it's going to be very close with my pore pressure. Now, the second, the other pressure that I'm going to calculate is going to be my fracture pressure, and it's going to be just as it's going to be the one that lead my rock to failure due to traction. So this fracture pressure, just as the shear failure, it's going to be by two reasons. There is going to be a low weight of my drilling fluid leading to an inferior fracture, and also due to a high weight of my drilling fluid leading me to a superior fracture. Well, in this case, I may have losses of well drilling, fluid while drilling, and it's going to be terrible economical losses, as many of you may know. So I need to have in mind this model when I'm drilling and also when I'm planning my drilling. So this is going to be represented here by this blue line that is going to be so close from my overburden gradient. Once I have this one, I'm going to finally get my